covariant dynamics of LQG. Being covariant dynamics, it's clearly some kind of analog of path integral. Okay, so let's come back to tradition and talk about path integral of gravity, four-dimensional gravity. Okay, so the working dimension in this lecture is always 4, 3 plus 1. Okay. No higher, no lower. Okay. And we know we can write down the partition function. Well, usually this partition function depends on the initial condition and initial condition or final condition, or more generally, boundary data. So here, I assume you have initial slice and final slice where you have 3 metric h in and h out. Okay, so and formally you can write down the path integral e to the I of the square, the Einstein double action, and you can add some higher order derivatives. Generally, there are higher order derivatives, and then there are boundary conditions that the basically G mu nu restricted on the initial slice, sigma in is HAB in, and G mu nu restricted to sigma out, the final slice is HAB out. Okay, so this is the scheme of path integral of gravity, and you can draw a picture for that. Okay, so this is your final slice sigma out, and this is your initial slice sigma in, and on the final slice you have your boundary data HAB out, and initially you have HAB in, so they are all 3 metrics, 3-dimensional metrics. And then in the bulk, okay, so you view that this is evolution and this is time direction. Okay, in the bulk you will have G mu nu. So this is the field that you are integrated. So these are sigma out and sigma in. They are all 3-dimensional slice, and here you have in the bulk you have M4, which is a 4-manifold. 4-dimensional manifold. And 4-dimensional manifold usually is called 4-manifold. Okay. And so here in this picture, it's clear that G mu nu is evolution, is given by evolution of 3 geometry. 3-dimensional geometry, from HAB in to HAB out. Okay. Or another word to say is it is a history. It describes the history from initial 3 metric to final 3 metric. And then this path integral, it sums over all kinds of evolutions. Sum over 4D metric with the boundary data, with the boundary condition. With the boundary condition being those 3 metrics, HAB in and HAB out. Okay. Or so because all these 4-dimensional metrics are histories, so this is actually summing over history. Histories of 3D geometry. Okay, so this is the logic of 4-dimensional path integral. It's all traditional and very standard understanding of path integral. But now we want to adapt this framework to quantum gravity. Okay. So being summing, now the key point is the summing over history of three-dimensional geometries. Four-dimensional geometry are just history of three-dimensional geometries. So now let's look at LQG. Okay, LQG. So we know that in LQG, 3D geometry are quantized. Quantized. Okay, we know that 3D quantum geometry are called spin network states. Okay, I assume that all of you should be familiar with spin network states, and they are given by the triple of gamma, which is a graph, and spin SU2 spin J on each link, and SU2 intertwiner on each edge. Okay. So this is a graph. So here graph consisting links and nodes. Yeah. So by the way, in the Spinfoam language, we have to adapt to a little bit different vocabularies in canonical formalism. Because for example, graph, I think you will call it edge and vertices. Yeah. But Spinfoam, we want to call it a link and nodes, because edge and vertices means something else. Yeah, so I will clarify that because, yeah. So we call this spatial spin network edge by links. We call spatial spin network vertices by nodes. Okay, so try to adapt to this new terminology. So this is spin links and intertwiner nodes, at nodes. Okay. All right. So now, yeah, because 3D geometry quantizes the spin network, then 4D geometry. Okay. So because classical 4D geometry has a history of three-dimensional geometries. So we know that when we quantize those geometries, quantum core geometry. Okay, basically quantum analog of G mu nu should be understood as history of spin network. Okay, so in the end, if you write down a path integral in the framework of quantum gravity, you should summing over histories of spin networks. You should take into account all kinds of evolution of spin network, yeah, and then summing over all kinds of histories of spin networks. And that is, yeah. So the history, okay, the history of Spinfoam is called a spin network is called a Spinfoam. So what is Spinfoam? Spinfoam, I guess, the history of spin network. All right, so give you a simple example. So what is the history of spin networks? You can consider a very trivial evolution of a spin network diagram. So this is the spin network diagram, trivalent, and you can add more valence in the spin network. And now you want to evolve it. This is time direction t. You want to evolve it, but then let's consider a very trivial evolution. So maybe it's good to change the color. So these give you the time evolution, and you will end up with the same spin network diagram as the initial. Okay. So this is a very trivial, simple time evolution of spin network, and you could add the spin labels J, and you want to be a very simple evolution, then so J1, J2, so the evolution doesn't change the spin, something like that. J3, and here you also have intertwiners, I1, I2, and so on. And so here you get the same thing, I1, I2. And this is maybe the simplest example of a spinfoam. So this is just a very trivial time evolution of spin network. And this time evolution doesn't really change anything. So there are a few key observations here from this diagram. That so you see that evolution. So here you have evolution of links, and you also have evolution of nodes. So let's first look at evolution of links, namely the spin network edges. Okay. So you see the time evolution of the link give you a phase. So the time evolution, because you add time dimension. So originally your link is one dimension, but you have time evolution. Then it gives actually a two-dimensional object. So what you get is what we call spinfoam phase. Spinfoam phase. And then because the link carries the representation label J, and then the time evolution basically gives this spinfoam label to the phase. So the spin J on link give you spin J on phase. And secondly, okay, this give you a picture that for spin network, your representation label J should color link, but in spinfoam, your representation label should color the phase. Now, the evolution of node. Okay, so node is zero-dimensional on spatial slice. Then the time evolution gives you one-dimensional object. So it gives the spinfoam edge. Okay, so that's the reason why in spinfoam we call spin network link and spin network node, because edge means here. So the time evolution of the node gives you spinfoam edge. So that's why we cannot call spin network edge anymore for spinfoam, because edge means the time direction evolution of the spin network node. Okay, so similarly, then you have intertwiner. For spin network, intertwiner I at the node, it gives the intertwiner on edge. Okay, so for spin network, the intertwiner is coloring the node, but in spinfoam, the intertwiner is coloring the edge because the node gets evolved. Okay, so this is some basic picture of spinfoam and its coloring. So it's a little bit different from spin network, but the difference is only upgrade one dimension. You have time evolution, so you color your spin to the phase, and you color your intertwiner to the spinfoam edge. Now, okay, so this is a very trivial time evolution, but of course we want to look at something more interesting. So let's add some structure to this diagram. Let me see. Maybe I can probably draw a different one. All right, so let me draw a different picture. Okay, the same final spin network and same initial. Okay, so now I want to add some interaction. Yeah. I want to make the diagram more interesting by adding something what we call spinfoam vertices. From vertices. Okay, so now I make 3 vertices, and then I also draw some spinfoam edge, okay, something like that, and some other edges like that. Okay. Note that these are the yellow lines are all spinfoam edges. They are different from spin network edges. Okay, so now so you see these gives you actually a non-trivial evolution. Yeah, non-trivial evolution, because if you consider some intermediate slicing, maybe I used again different color. Okay, so these I will call sigma intermediate. Okay, so you will see you will actually get on this spatial slice a different spin network, because it will cut the spinfoam edge here, here, and here, and this spin network edge, this spinfoam edge here. Okay, you see that there's additional edge created. Okay, maybe so here there's additional edge created because there's a spinfoam phase. Okay, so for this picture, you will see the time evolution starting. Okay, so this is your sigma in. So your diagram, your spin network is like that. And then after some time evolution, you get a sigma intermediate. Your spinfoam graph is like that. You get additional edge here, and then so finally you come back to the same spin network diagram. On sigma out. Okay. So here you see from this diagram, you see some non-trivial process. So it's the logic is very much like Feynman diagram. So I mean, if you make your diagram more complicated, then you get some more non-trivial process on your diagram. And so here you see the key point I add to the previous diagram are something what we call vertices, something we call vertex, spinfoam vertex. So you see that compared to the previous diagram has no trivial evolution, yeah, because yeah, in the middle there's no vertex, but the lower diagram has non-trivial process because I add 3 vertices. Yeah, these yellow vertices here. Okay, so here the key point, the punchline here is that yeah, so you get non-trivial process. So if you have spinfoam vertex. Yeah, so this is also the reason why we have to call spin network node instead of spin network vertex, because there's a spinfoam vertex play the key role in spinfoam. Yeah. So don't confuse this don't confuse with spinfoam vertex to the spinfoam to the spin network node. Okay. So this spinfoam vertex actually, so you see it's an interaction between, it mediates, well, it gives the interaction among edges and phases. Okay, because this, for example, a typical spinfoam vertex has 5 edges. So this is what I draw on here, and we will often study this kind of spinfoam vertex. So for any two, so there are 5 edges joining at this vertex, and then for any 2 edge, there is a face. So for any 2 edge, there's a face here. There's a face here. Yeah. Okay. So basically, you have 5 edges joining at the vertex, and then you also have 10 faces, attached to this vertex, and all these representation labels on the faces. Remember, on the face there are representation label. On the edge, there are intertwiners, and all these are quantities that are interacting at this vertex. Okay, so that makes things more interesting. And then the result of this interaction that you will see later on are basically creating geometry. Creating 4D quantum geometry. Okay. All right. Okay. So these are basically some very broad overview of spinfoam, and give you some motivation and some geometrical pictures. Any question up to here?
And these vertices are then basically can be split up in these partner moves, so these basic steps of creating edges or.
Yes, you could add packing moves, make packing move act on those vertices, basically, but that's change from one spinfoam to the other. So packing move is basically changing.
So one of these time steps, basically.
Not exactly. So let's see. Maybe you can keep this question. Ask again later on. All right. So let's come to the next. So I'm giving you a simple example of spinfoam, simple example of constructing spinfoam model. Yeah. So let's talk about a simple spinfoam model. Spinfoam model of what is called BF theory. Okay. So this give you a firstly give you a simple example of how to construct the spinfoam amplitude from scratch. And secondly, this theory is closely related to loop quantum gravity. So basically, probably you have heard what is called EPRL spinfoam model that is very popular right now. It is constructed based on BF theory, based on some modification of BF theory. So let's first talk about BF theory. Okay, so BF theory is a simple topological quantum field theory. Classical, let's first look at classical BF theory. Okay, and you may wonder who is Mr. B and who is Mr. F. Okay, so but Mr. B is a 2 form. It's a D-2 form, and F is 2 form. Okay, all right. So they are not misters. They are just fields. Okay, so let's talk about BF theory, and then BF theory depends on a structure group. Yeah, and let's assume this structure group G is a matrix Lie group. Okay, and this BF theory is defined on a D-dimensional manifold. So let's call it MD. So in the end, we will restrict to D equals to 4, but let's keep it general for now. D manifold. And I can write down the action as BF equals to MD trace basically B wedge F. Yeah, and this B is G valued D-2 form. And this F is a curvature 2 form. Of the connection, of G connections. So here, basically, the field content of BF theory is this D-2 form B, and also a connection. So a connection. Okay. Yeah, and F mu nu. So F is just the curvature relates to the connection A. So this gives you the explicit expression. And then this, let's assume that B and F, they are in the fundamental representation, and then this trace is just like matrix trace. It's an invariant bilinear form. Okay, and so these are Mr. B and Mr. F. Yeah, and so you see this this action is really simple, and it's a topological quantum field theory. Namely, it has no local degree of freedom. So this BF theory is a topological field theory. Topological field theory. Yeah, so you can study the variational principle. Look at equation motion of this theory, and the equation motion is very easy to see. That firstly, you will get the covariant derivative of B equals to 0. So this dA means the covariant derivative act on the Lie algebra valued B. And secondly, so this is first equation is variation with respect to A. Yeah, do an integration by part. And the second equation is variation with respect to B, but the action is linear to B. So you will get just FA equals to 0. Okay, so it means the connection is flat. Yeah, on the manifold. And from this equation, you can see that there's no local degree of freedom. Okay, by the way, so I have to mention this. I have to mention the gauge invariant. So there's a gauge invariant. Gauge, oops, sorry. It's a gauge invariant. So firstly, you have gauge invariant of the connection of the gauge potential. So and same the joint action of B. So this is the first set of gauge transformation. A transform like a connection. Okay, so G is a local gauge transformation. Okay, and there is a second set of gauge transformation. So and first set of gauge transformation is more or less manifest because yeah, A transform like a connection, then F transform like a joint representation. Yeah, and B is transformed in the same way as a joint representation, but this trace is invariant by linear form. So the action is invariant. And there's a second set of gauge transformation, which is the translation of B plus DAF. And A doesn't transform. So this is another set of, well, see, this F is a D-3 form. Again, Lie algebra valued. You can. This is also more or less manifest because if you make this translation of B, and then make an integration by part of this dA, and then this dA act on F, but this is 0 by the Bianchi identity. So you add this term, then do an integration by part, and then dA act on F, but that is 0 by the Bianchi identity. Okay, so this is another gauge transformation. Now let's look at this equation of motion, and to see that there are really no local degree of freedom. Yeah, so let's consider some topological trivial d-dimensional manifold, namely, let's say MD is just RD, so it's topological trivial. Okay, and then so the second equation is a flat connection. Fa equals to 0, second equation of motion, so it means a flat connection. But because Rd is topological trivial, so the flat connection is just a trivial connection up to gate transformation. So flat connection means A equals to 0 up to gate transformation. Up to gate transformation. Okay, so this is yeah. So basically, you see there's no degree of freedom for A. Yeah, A is just a gate transformation. Now, then let's look at dB equals to 0. So let me zoom out a little bit, so you can still see the equation. Okay, so now this dB equals to 0 equals to 0, but A is 0. Okay, so this is just the covariant derivative just becomes an ordinary exterior derivative. dB equals to 0. It means that B is a closed form. B is closed. Yeah. But since Rd is just a topological trivial, so the closed form means it's exact. It is the exact form. So B is closed implies on a topological trivial manifold. It means B is also exact. So namely, B equals to dF. But you see, dF is just a gate transformation, because look at the second gate transformation above. So it just means that B equals to 0 up to gate transformation. Okay. So you see, there is really no local degree of freedom because, yeah, at least locally. So I mean, any manifold locally it is Rd. Yeah. So on Rd, the equation of motion implies A equals to 0 and B equals to 0. There's no degree of freedom. Yeah. So that's why we call it topological field theory, because there's no local degree of freedom. The only degree of freedom are basically either on the boundary or different kind of topological non-trivial D manifold. Yeah. So this is a very typical feature of topological quantum field theory. Okay, so this is a classical BF theory. So any question about this? I hope it's all clear. Okay. Let's look at quantum theory. Let's look at quantum theory. Okay, so this is the partition. We use path integral quantization of BF theory. dB A e to the I. Okay, so now the action is linear to B. Okay, so you can we can just integrate out B. Yeah, we get a delta function. A. A. So basically, the quantum theory of BF theory is just integration. The partition function is just integration of flat connection. Integral over flat connection. Flat connections. MD. Okay. All right. So now, but you see, this is a formal expression, as always for path integral. But now we want to make sense this path integral. Okay. All right. To make this formula better, so we have to replace some local object like curvature by something a little bit non-local. Namely, we should define holonomies that replace this curvature. Okay. So to make this formula better, let's consider consider loop holonomy. Loop holonomy in D manifold. Okay, and let's draw a loop in D manifold, starting certain base point, and I call this loop L, and then there is a two surface, so it circles around the two surface S. So L is a loop, and S is a two-dimensional surface. Two surface such that boundary of S is L. Okay, and then we have something called non-abelian Stokes theorem relating the holonomy along the loop. So this is by definition the path ordered exponential of the connection A, but this actually relates to the curvature, something called the surface ordered exponential, e to the exponential of curvature integrate along on S. This is not very much precise. This is actually relates to certain parallel transport. So this is called the non-abelian Stokes theorem, and you can easily see the abelian analog. In case there's no, in case you consider abelian group, then there's no path ordering, there's no surface ordering, and then there's no this G inverse, and what you have is just the usual Stokes theorem. But when you consider a non-abelian gauge group, you have this formula, which is non-abelian analog. Non-abelian Stokes. Okay. I don't have time to prove it, but you can find the proof online. You just Google non-abelian Stokes theorem, you find the proof. Okay, but the point is that you find that in case for the flat connection, f of A equals to 0, it is equivalent to say that this holonomy of A equals to identity. So that's the punchline for any loop. So in that sense, connection being flat is equivalent to say that for any loop, the holonomy is identity. For let's say topological trivial manifold, or for any contractile, more precisely for any contractile loop, the holonomy is identity. All right, so now we can replace the partition function by using holonomy. So the delta function of f is replaced by delta function on the group of holonomy, of contractible holonomies. Okay, but this formula is still not very nice because this product is over all the loops. So it is an uncountably infinite number of loops in this product. So this formula is still formal. So let's do something more by regularizing this path integral. So in that case, let's look at more specifically the dimension equals 4, and the group, let's say, is just SU2. Okay. In the following, we will just restrict the 4 dimensions and the gauge group to be SU2. And to regularize this path integral, let's introduce a discretization of the 4 manifold, which is a triangulation, or usually it's also called simplicial complex. Simplicial complex in 4D, or it is the same thing to say that it is a triangulation. Triangulation of 4 manifold. So introducing triangulation or some discretization of 4 manifolds are some very basic tool to study topological quantum field theory. Yeah. All right, so let me firstly take this opportunity to introduce and to tell you some basic topology of triangulation. So, well, this will be very important when we talk about Spinfoam. We need to first familiar with some elementary topology of 4-dimensional triangulation. Okay, so let's look at elementary cell. Okay, the basic cell in 4D triangulation. So this is the most important property is that this is something called 4-simplex. Okay, to understand Spinfoam, you have to be very familiar with the topology of 4-simplex. So this is I'm drawing a projection of a 4-dimensional 4-simplex on the blackboard. Yeah, so this is a 4-simplex. Yeah, and of course I can only draw a 2-dimensional diagram, which is a projection of a 4-dimensional object. Yeah, so it has, okay, so you can, it has 5 vertices. 1, 2, 3, 4, 5. Okay, so you can try to make some analog. So you see that on 2 manifold, a simplex is just a triangle. Yeah, it has 3 vertices, 2 plus 1. And in 3-dimensional, a simplex is a tetrahedron. It has 4 vertices, 3 plus 1. Yeah. And in 4-dimensional, it's a 4-simplex. Yeah. It has 5 vertices, 4 plus 1. Okay. Yeah, it's not just the analog, because the reason is that if you want to span if you're starting a vertex, you want to span a 4-dimensional vector space, you need 4 edges. Yeah, so you can see that at each vertex, you have 4 edges, giving you the 4-dimensional frame. And then, yeah, for any vertices, you have this 4 of the 4 axes, then you end up with 5 vertices. In total, 5 vertices. Okay, so this is a simple picture of 4-simplex. Okay, and by looking at this 5 vertices, you can see the boundary of 4-simplex. Okay, so 4-simplex is a 4-dimensional manifold. The boundary of the 4-simplex is a 3-dimensional manifold. Okay, yeah, and then on the boundary you have some tetrahedron. Yeah, so 4-simplex on the boundary. Yeah, 4-simplex is 4-dimensional simplex, and then the boundary is a closed surface. Yeah, it's a closed surface, but it is also triangulated by some 3-simplex. Yeah, how to see this? Because you can pick up any 4 points. Okay, so you, for example, 1, 2, 4, 5. These 4 points. Maybe I use a different color. So you can see there is a tetrahedron. Okay, so look at the yellow line. So you see a tetrahedron. Okay. Therefore, whenever you pick up 4 points out of 5, you get the tetrahedron. So, and this tetrahedron is living on the boundary of the 4-simplex. Okay. So in total, how many tetrahedra? So they are C. So it's just a simple combinatoric number. So this is for any 5 points, you pick up 4. How many choices? There are only 5 choices. 5. There are in total 5 tetrahedra. Okay. And similarly, you can see. Okay, so you can see that the boundary of this 4-simplex is a closed surface triangulated by 5 tetrahedra, and then these 5 tetrahedra are glued, yeah, to form the closed surface, and 2 tetrahedra are glued through a triangle. Yeah. So then you can count how many triangles on the boundary. how many triangles? Whenever you pick up 3 points out of 5, you get a triangle. So in total, you get combinatoric number. How many ways to get 3 points out of 5? So equals 10. Okay, so in total, there are 10 triangles. 10 triangles. Okay, so this counting is very important, and to understand 4 simplex, these are very important facts. So keep in mind that on the boundary of 4 simplex, there are 5 tetrahedra and there are 10 triangles. Okay, and in the end, these 10 triangles will be colored by spin because they are faces, or more precisely, are dual to faces, and tetrahedra will be colored by intertwiners. Okay, so which means for the spinform amplitude of the 4 simplex, it depends on 5 intertwiners, each for 1 tetrahedron, and 10 spins, each for 1 phase. Okay, so this is some basic intuition. Okay, I will come to that later on. All right, so now this is our basic topology of the 4 simplex. So when we consider for the simplicial complex, simplicial complex, you just glue 4 simplices. Glue 4 simplices by identifying a pair of tetrahedron. Okay, so a simple example, gluing 2 4 simplices, you can they share a single tetrahedron. So this is tetrahedron, and then you add 1 point here, 1 point on the other side. So of course, this is not so easy to draw because this is drawing. You are drawing a 4-dimensional object projected on the plane. So these are basically you have 2 4 simplices sharing a single tetrahedron. Okay. Well, because usually a 4-dimensional picture is very difficult to draw, sometimes it is convenient to introduce something called the dual complex. So this will be also important for spinform. So so the simplicial complex has a dual complex, has a unique dual complex. The complex associate the unique dual 2 complex. Complex. Okay, so let me describe this this duality. So let's see on the left is the simplicial complex. Complex, and on the right is the dual 2 complex. 2 complex. Okay, and then in simplicial complex, there are 4D object, which is a 4 simplex, and you have 3D object, which is a tetrahedron on the boundary of 4 simplex, and then you also have 2D object, which is triangle on the boundary of tetrahedron. So mathematically, being a complex means you have a chain that you have here is a 4 simplex, and then the boundary of 4 simplex is tetrahedron, and the boundary of tetrahedron is triangle. Right? Okay, so you have 4D object, 3D object on the boundary of 4D, and you have 2D object. and the dual is very much similar to the duality of differential form. So the 4D object, the dual of a 4D object is a 0D object in a dual 2 complex. The dual of 3D object is 1D object, namely an edge. So okay, so dual of the 4D object is a 0D object, is a vertex. So this is precisely the Spinfoam vertex I mentioned earlier. So this will be the vertex. Okay. And the 3D object is dual to a 1D object. It is the edge that I mentioned earlier. And 2D object is dual to a face. It's another 2D object. It's the face. Okay. So 4D on the left is the 4 simplex. It's tetrahedron. Triangle. Okay. So that's why in Spinfoam literature, we often mix up the simplicial complex and simplicial complex terminology and dual 2 complex terminology. So sometimes we call it 4 simplex, and then we call it vertex. It's the same thing. And tetrahedron and edge is the same thing. And triangle and face is also the same thing. Okay. All right, so let me go into detail how these two are, the left and right, are related. Okay, so let's first look at 4D and 0D duality. Okay, so here this is the 4 simplex.
Sorry, I have a question.
Yeah.
Is it a node or a vertex?
Vertex.
A vertex.
A vertex.
Because I understood that the vertex is when you have like an interaction.
Yeah.
So it's like
it is. Yeah. It is. Yes.
Okay.
Yes. Yeah. It's corresponding to a 4 simplex.
Okay.
Right. Okay. What we call so later on we call Spinfoam amplitude of a 4 simplex is the same thing to call it vertex amplitude.
Okay.
Yeah. So that gives the interaction of quantum geometry. Right. So now 4D, 0D, and 4 simplex. So then the dual of the 4 simplex, it is a vertex at the center. At the center of the 4 simplex. Okay. So namely, you have a 4 simplex. For every 4 simplex in the triangulation, you just put a point in the middle at the center. So that is a 0D. That's the vertex in the dual 2 complex. Okay, so very simple. So then the 3D 1D duality. Okay, a tetrahedron. It is, well, now the tetrahedron, more precisely, it is, so a tetrahedron shared, let's say tetrahedron shared by 2 simplices, two 4 simplices. Okay, because when you glue 2 4 simplices and they share a single tetrahedron. And the dual of it is an edge connecting 2 vertices. So you see, it's quite related, because whenever you have in the simplicial complex side, you have 2 4 simplex sharing a tetrahedron, and then in the dual complex side, you have an edge connecting 2 vertices. Yeah, so these 2 vertices are due to 2 4 simplices. Okay. to visualize it, let's use this diagram. So here you get two four simplices sharing a single tetrahedron. Okay, and now at maybe better change color. So this vertex is orange, and so you have four simplex on the left and four simplex on the right. You have two vertices, right? And you just draw an edge connecting these two vertices. Yeah. And this is the edge dual to the tetrahedron shared by these two four simplices. Okay, is that clear? Now, 2D duality. Okay. So this is a triangle. In the simplicial complex side, this is a triangle shared by a number of four simplices. Okay, this is just like in 3D, if you go lower dimension, in 3D, a 1D object, a 3D triangulation, a 1D object, which is the edge on the boundary of tetrahedron, is usually shared by several tetrahedron going around. So it's going higher is a two-dimensional triangle is shared by multiple four simplices. And then this is corresponding to a face with n vertices along the boundary of the face. Okay. So you can see that you can draw the dual picture. So it's too hard to draw the simplicial complex picture, but you can always draw the dual picture. Let's say this is the face F in the two complex, and then you see on the boundary there are many vertices. Okay, you see, and each of the vertex are dual to a four simplex, and two vertices are connected by an edge. It means that two four simplices are glued through a tetrahedron. Okay, so here, so for each vertex, you will have a four simplex. It's dual to a four simplex. So here they'll get another four simplex. Okay, and these four simplex are glued through a tetrahedron due to this edge. Okay, so I hope this give you a good picture. Okay, so this describes the duality between a simplicial complex and a dual complex. So whenever we say four simplex, it corresponds to a vertex. Whenever we say a tetrahedron, it corresponds to edge. And whenever we say a triangle, it corresponds to a face. And here the object vertex, edge, and face are the ones I described earlier for the Spinfoam, where the Spinfoam lives. Okay. Now, okay, so maybe give you a little bit more complicated example. Let's say this is the example. Let's draw a complex like that. So this is an edge. So this is in the dual two complex. You get an edge shared by multiple faces. Okay. Then you see in this complex, in this two complex, you get two vertices. You got two vertices. Okay, so each of the vertex is 5-valent. It's a 5-valent vertex. Now this by duality, so each of these vertex is dual to a 4-simplex. Okay. So you got two of these vertices. Okay. Maybe it's a question for you. Can you tell me what is the dual picture? What is the picture in the simplicial complex? What that describes? You have some intuition. You have two 4-simplices and two vertices connecting them by an edge and multiple faces. And this is precisely the picture above. This is just this picture above. Yeah. So you have two vertices, two 4-simplices glued, connected by an edge, means that two of them are glued by a tetrahedron. So 4-simplex. Okay. So this is an edge shared by an edge connecting two vertices. It is the same as two 4-simplices means a tetrahedron. Shared by two 4-simplices. Okay, so this is something we mentioned earlier, but why they are 4 faces? Because tetrahedron has 4 triangles. So there are four faces connecting to the edge. Means that tetrahedron has 4 triangles. Four triangles on the boundary. Okay, I hope this helps. So
this means you have more ways to do them together, basically.
Oh, there's a single way too. So here these two vertices are connected, yeah, by a single edge. It means this edge has a tetrahedron, corresponds to tetrahedron. But tetrahedron has 4 faces, yeah, and this it means that you have 4 faces, has 4 triangles. Yeah, but now in the dual complex, it means that you have 4 faces, 1-to-1 correspond to these 4 triangles. Yeah, and these are these 4 faces that I draw. So which means that for any tetrahedron in this simplicial complex, it corresponds to a picture like that. It's not just an edge connecting 2 vertices, but this edge is a boundary of boundary of 4, exactly 4 vertices, 4 faces. Okay, I hope this helps. And also maybe it's also visualizing by the earlier picture that suppose you have a spatial slice cutting this foam, cutting this spin foam. Yeah. So remember that the edges is always goes to time direction, more or less, roughly speaking, always goes like time direction. And then if you use a special slice to cut, what you get is a spin network. Yeah. So what you have on the spatial slice is a 4-valent spin network. It's a 4-valent spin network. That's also dual to a tetrahedron. So which means when we talk about a simplicial complex and Spinfoam on the simplicial complex, the spin network that we are considering are always 4-valent. All right. Okay, so now let's I think we have
yeah. We are now on the dual.
So this is a dual picture, right?
So if so is the dual of the spin network, or it is
the spin network is the dual. It's on the dual.
Okay.
It's always the dual. Yeah.
Okay.
Yes. Yes. Maybe if you have ever seen that, so a intertwiner, a 4-valent intertwiner. So this intertwiner I. So here you get spin J, J1, J2, J3, J4, and this corresponding to a tetrahedron. This quantizes a tetrahedron. I'm not sure if you have this. Probably you have seen this, right? So the dual picture is a tetrahedron. So and then this edge, so the area is given by J, and the shape of the tetrahedron is given by this intertwine. So quantization of the shape of the tetrahedron is given by the intertwine. Okay, so this is, you see, this is also a dual picture, but in 3 dimensions. Okay. Okay, so now let's apply this technique to BF theory, to derive this Spinfoam. So now let's regularize the passing through. Passing through. So remember, previously we end up with this kind of okay. We end up with this passing through of we still have a uncountably infinite product of all the loops. And now we have a triangulation. Let's say we put a triangulation on the 4 manifold, and then we say that all these loops are going around all the dual phases, all the dual phases. So these we rather consider dA product of all the dual phases. F are phases in 2 complex. And then this L, the loop is on the boundary of the dual phase. Okay. And this measure, this passing through measure, we take is just a Haar measure. Haar measure. So dA is product over all the dual edges. So these are edges in 2 complex. All right. So draw a picture of the dual. This is let's say this is a typical dual phase, and then this phase is oriented because we have to define holonomies along the boundary of the phase. So this phase is oriented, so all the edges on the boundary are oriented. Okay. So namely, we have to choose a orientation on the phase, on each phase. Okay, so more precisely, the two complex that we are considering are oriented two complex. So this also relates to the spin network we study are based on oriented graphs. All the edges has orientation. So that's why we can define holonomy. Okay, and then this. So now we see we have regularized this path integral. We can make sense everything in this path integral, and the measure is Haar measure. And in these two complex, we assume there are only finite number of edges, and there are finite number of phases. So which means all this product, the measure product in the measure, and the product of delta function are make sense. Are always finite product. And the delta function on the group is also makes sense as a distribution, of course. So let's say G is SU2. So this is the formula. There's a formula for the delta function. Is can be written as sum of characters, dimension of the representation, and character of the representation. And here the character is just the trace in the J representation. All right. So this is the formula for the delta function, and now this we have to evaluate the delta function for the holonomy along the boundary of the phase. Okay. So this delta function of H partial F A. Now let's suppress A. Yeah, so holonomy along the boundary. Yeah. So this is you just plug in the formula. So we actually only need to consider the character. Let's say the character J of that, because this is just a trace. Yeah, just a trace. So this is just trace J holonomy along the boundary. And then you can factorize the holonomy to the holonomy along the edge. So each of the edge is HE. Let's make some numbering. So this is E1, E2, E3, E4, E5, E6, and so this is along each edge you have HE. So what you get is basically the representation matrix. So I call this representation pi. Okay, H E N, yeah, n equals 6 for this diagram. Pi J KL H E n minus 1, and so on. In the end, it is trace. You have to close the loop. PM. Okay, so the first index and last index is the same, means that there's sum. So this is really just a trace written in terms of the representation matrices. Okay, so here I skip the summation symbol, but because here we use just Einstein summation. So here K and K means sum over K, and M and first M and last M means sum over M. So here's so that's why we make a trace. All right. So now we plug in this formula in the partition function. So that equals to just the integral finite product of Haar measure product for all the phases, sum over J. So now you see you get for each F there's a J, there's summing over J, because for each F there's a delta function, and decomposing delta function you get characters, and each character has a J. Yeah, so here you have to label J by F. So that's what I said earlier. Representations are associated to phases. Infinity, and then you have dimension JF. And then there are string of pi's, JF, MF, KF, EN. Okay, we just plug in this formula. Now, now let's take carry out this integral of over the group. Okay, so let's pick up this integral. But now you see, you can this integral involving the integration over holonomies along a single edge. Okay, so which means you need to pick up the local structure of a single edge, and yeah, that corresponds to that integral. Okay, what is the local structure of single edge, and which is exactly this one, exactly this picture. Maybe let's just copy this picture. And remove some useless stuff. Okay, yeah. So this is an edge that we are interested, and we know that along this edge there's a holonomy. Yeah, this HE. Yeah, remember this HE coming from the holonomy around the face, and then these face are bunch of edges, and then for each edge there's a edge holonomy. Yeah, so here there's a HE, but now like we studied earlier, that for this edge there are 4 faces, so which means this HE is shared by 4 faces, 4 face holonomies, and each of the face has a holonomy. So here you get F1, F2, F3, F4. Okay, and all these 4 faces has loop holonomy entering this integral, and the face holonomy, yeah, they share a single edge, this HE. Yeah, so which means this integral will involve in 4 factors, and more precisely 4 of these pi's. So each loop holonomy will have 1 factor of this pi involving this edge. Okay, so maybe let me write down the integral so it is clear what is happening. So the integral is just the HE. So I forget about this mu h, the Haar measure. I just call it dHE. Okay. So this is pi J1 and 1 and 1 HE, pi J2 M2 N2. So this is the integral that involved in this calculation. Okay, so these 4 pi's are coming from the loop holonomy of these 4 faces. Yeah, so this there's only a single factor of pi in this loop holonomies involving this phase participating in this integral. Okay, is that any question about this? So that's basically the only non-trivial integral that one needs to compute.
The orientation of the sketch is always the same.
Oh yeah, let's consider simply the case that the orientation is the the same. Of course, you can have sometimes you may get inverse somewhere, then you get the intertwiner has a little bit different representation.
So it's allowed that one phase.
That's right. That's right.
Uncompatible orientation of these edges.
That's right. That's right. That's right. Yeah, yeah. It's allowed that you may have different orientations. Then sometimes you get inverse in these factors. Then the result change a little bit, but the scheme is the same. We didn't make any break. Do you need any break, or it's fine? So we can continue another half an hour, 20 minutes or something. Okay, so this guy, actually, it is because Haar measure is invariant integral. Haar integral is invariant integral. So this guy actually defines a projection operator. J1, J4. Four. Okay, so this is a projection operator because projection onto the invariant subspace of SU2 representation. No. You can check by yourself. Probably this can be a exercise for you that by using the invariant property of the Haar measure, so you can show that this is a projection operator. Projection operator onto the intertwiner space. Space invariant SU2 VG1. Let's call the representation space corresponding to spin J is I call it VJ. This is a projection operator onto the invariant subspace or the intertwiner space. Okay, and then because it is a projection operator, you can write this projection operator in terms of the basis in the intertwiner space. So this is equals to I. I denotes the basis in the intertwiner for R. To see this is the projection operator, you only need to show that this quantity is invariant in the M index and also in the N index. So this is M index give a tensor product representation of SU2. N index corresponds to another tensor product representation of SU2. You only need to show that this tensor product representation corresponds to M index, corresponds to N index, are invariant. Yeah, by using the invariant property of Haar measure. This is very easy to show, I think. Okay, and this is a projection operator. That's why in quantum mechanics, there's a standard way to write a projection operator by Bra and Kit. Yeah, so this is Kit, and this is Bra, this is a Kit. So you can write in terms of basis of intertwiners. All right. So now you see that by this integral, you associate every edge a projection operator. So now, well, let me better write it down. I is basis of intertwiner. Basis of intertwiner, and now the integration shows us that each edge is associated with a projector. I call it PE, J1, J4, MN index. All right. Now, okay, so each edge, so basically you get the structure coming from this BF theory that on each edge you have a projection operator. But now, because all this integral coming from phase holonomies, and all those indices m and n, they are actually contract with other indices of other pi. So here, what we did are just pick up those pi factors that involved in this integral and then compute the integral, right? But those pi factors has indices m and n, but all these m and n are contracting with other pi factors because it comes from loop holonomies. Okay, so which means that what you get, yeah, after the integral, here we have already carried out all the integrals, right? Because BF theory only has this group integral. We carry out all these integrals, we get all the projection operators, and in the end, the amplitude or the partition function, you can just write the results. So actually, we already have we did all the computation already. So we factor out, we put out the summation over all the spins. Yeah. And then for any f, there is a dimension factor coming from delta function. Okay. And then there's a trace of product of all the edges and projection operator. Yeah, that's it. It is just the spinfoam amplitude for the BF theory. And this trace just means that contracting indices. Indices according to phases. Okay, so this trace just means we should, once we have this projection operator, we have to contract their indices because according to because they're coming from the trace of a loop holonomy, yeah, because they're coming from these pi's, and trace holonomies have those contracting indices. This kf has to be contracted to the kf of the neighbor. Yeah. So this contraction, I just call it a trace. Yeah. It's a little bit implicit, but I hope you get the structure. But now there's a more explicit expression. By instead of using projection operators, we extract local structure at the vertex. So here, this formula is like you extract the local structure at edges. So each edge corresponding to a projection operator. You can also extract the local structure at the vertices, which you can have more explicit expression for this partition function. And how to see it? Because if you look at the edge, this edge is of course connecting two vertices, and this edge, as I said earlier, there is a projection operator, but the projection operator is the sum over intertwiners, I star I. Okay, so let's let me see. Let's orient it in this way. Okay, so then it's intuitive to associate an intertwiner 1 to the beginning of the edge, beginning point of the edge, and 1 associated with the end point of the edge. So the structure along the edge, you can say it is a projection operator. You can say there are 2 intertwiners, I and I star, 1 at the beginning, 1 at the end. Yeah. Or you can say that this I is associated with the beginning part of the half edge, and this I star associated to the end point and the end part of the half edge. Okay, so you see that's also the illustrating the idea at the beginning that the intertwiner associated with edge, right? Before, by the evolution of spin network, the intertwiner relates to an edge, right? And the spin relates to phase. So here I illustrate why spin relates to the phase, why spin associated to phase, and then this projection operator, the relation between projection operator and intertwiner, illustrating why the edge associated with intertwiner. Okay. Now let's look at the local structure of a vertex. Okay, this is a vertex, and this vertex has 5 half edges. 5 edges, but because you can associate the other half to the neighboring vertex. Yeah. So let's say each vertex associated with 5 half edges. Yeah, and all these half edges. So let's, for simplicity, let's orient them just outgoing. Of course, you can change them. Yeah. So here, basically, we have divided this edge into half. That's why you have 2 intertwiners. And then this intertwiner, you have 5 intertwiners. 2, 3, 4. 5. Okay, you have 5 intertwiners, associated with vertex, yeah, in the neighborhood of the vertex. Okay, and then these 5 intertwiners are contracted one to the other, because you have any 2 edge, so you have a face. Okay, so which means, remember that whenever you have a face, you have face holonomy, and face holonomy give you the contraction of those pi indices, give you a contraction of the index. So which means all these intertwiners has to be contracted according to the face, yeah, according to the face orientation. So which means that, so here you will have a face, so this should give you a contraction of index, and here give you a face, and this should give you another contraction of index of those intertwiners. Okay, so in total there are 5 edges, give you 10 faces, and it means that you have 10 contractions. Okay. Now there is a graphic way to have this contraction. That, so you can draw a intertwiner using a spin network diagram. You can draw a 4-valent intertwiner I like this. So J1, J2, J3, J4. This is a 4-valent. You draw this like a 4-valent intertwiner, just like we draw a spin network diagram. Yeah. Although on each edge there is no holonomy. So this equals to I J1, J4, M1, M4 magnetic index. So this is a tensor intertwiner, invariant tensor. And illustrating this contraction given by this those phases, what you have is, you see, so every intertwiner is contracting with one index with a neighboring intertwiner. Okay, so you have in total 5 intertwiner. They are mutually contracted. So what you get is a 4-simplex diagram, but don't confuse this diagram with simplex in the simplicial complex. So this is just showing the contraction of the intertwiner. 1, I2, I3, I4, I5. Yeah, connecting the line means contracting the index in a SU2 invariant way. So each edge carrying the label J1, J2, J3, J4, J5, J6, J7. Okay. Okay. So in total, on this spin network diagram, there are 10 spins and 5 intertwiners. Okay. And the result of the contraction is called 15J symbol. So it's called 15J. 15J symbol. So this is just a yeah. Don't confuse this diagram with the 4-simplex in the simplicial complex. It just shows the, or I'm more precisely, this is the dual diagram of the dual spin network diagram of the 4-simplex. Each intertwiner. So this is just showing the contraction of intertwiner, invariant tensor. And the result of the contraction, it is a invariant object, is a number. If you give me 10 spins and 5 intertwiners, the contraction give you a number. Yeah, this number is called 15J symbol. Yeah, it depends on 15 J's, 10 of the spins, 10 of the SU2 spins, and 5 of them are intertwiners. So that's why we call it 15. And this is the vertex amplitude of BF series. Okay, so now we can give a much more explicit expression of the partition function for the BF. Okay, so these, you should sum over all the spins coloring the face, sum over intertwiners coloring the edge. Yeah, this sum coming from the projection, come from the projection operator, because projection operator is a sum over intertwiners. Yeah. Remember, projection operator is a sum over intertwiners. Then you this sum over, this give you the sum over intertwiner along all the edges, and then this there is a product of all the faces, dimension of the representation. Yeah, this is coming from the character. When we write the delta function in terms of character, there's a dimension, and then for any for any vertex, there is a 15J symbol. Yeah, so here we product over all the vertices, and there's a 15J symbol associated to the vertex. Okay, so this is the explicit expression for the BF partition function in terms of Spinfoam in the Spinfoam picture. So this dimension of JF, this is something we call phase amplitude. So because this is amplitude associated with all the phases, and this 15J, it is the vertex amplitude. It is the vertex amplitude. Okay. And for the Spinfoam that we are interested, like related to quantum gravity, the amplitude factorized in a very similar way in terms of phase amplitude and vertex amplitude. Basically different, the structure is more or less the same. So the difference between different Spinfoam amplitudes are just a different choice of vertex amplitude and phase amplitude, for example. Yeah, so here, I just give you a result for the BF series, and more precise, well, there's a name for this model. It's called the Augury model. So this is defined by Augury in 90s probably, and this has some property as a topological invariant. It's not exactly a topological invariant, but it has some similar property as a topological invariant. Yeah, because it's easy to understand, because we start from a BF theory, which is a topological field theory, and in the end, one should get something relates to topological invariant. Okay, any question about this? So this is the BF theory. Okay. We have another 10 minutes. Hey, I think this is a good point to stop, I think. So next time, tomorrow, I'm going to just talk about the ETIL model.